The question that drives this entire discussion is deceptively simple. What does it mean to take the factorial of 1/2? Factorial, as most people know it, is an operation defined for positive integers. You take a whole number and multiply it by every positive integer below it. But what if the input is not a whole number at all? It turns out this question was answered long ago, and the answer involves one of the most important functions in all of mathematics. The factorial function can be extended far beyond the positive integers using a construction known as the gamma function, and when that extension is applied to the input 1/2, the result is the square root of pi divided by 2, a number that contains pi despite having nothing geometrically circular about the original question. The gamma function is defined by an integral. You integrate the expression t raised to the power of s minus 1, multiplied by the decaying exponential, e to the negative t, as t runs from 0 to infinity. This integral converges whenever the input s is a positive real number, and it produces a smooth, well-behaved function that agrees exactly with factorial at every positive integer. That is the classical definition attributed to Euler. But in this video, we will not be using this integral at all. We will reach the same destination by a completely different route, one discovered by Gauss, that requires only limits and elementary algebra, with no calculus whatsoever.
To make this concrete, the factorial of 5 is 1 times 2 times 3 times 4 times 5, which gives 120. Simple enough. This is a function that takes a positive integer and returns its factorial. We can think of this as a function. You input a positive integer, and the function outputs its factorial. The domain right now is restricted to positive integers. That is where factorial lives by its original definition. The question we want to answer is whether we can build a new function that agrees with factorial at every positive integer, but is also defined at non-integer inputs like 1/2. To give you the destination before the journey, when the function is properly extended, the input 1/2 produces the square root of pi divided by 2. This is the result we are building toward, and by the end of this discussion, you will understand exactly why this number appears and where the pi comes from. To understand how such an extension is possible, it helps to remember that mathematicians have done something very similar before, with exponentiation. When exponentiation was first invented, it was purely a shorthand for repeated multiplication. 2 to the power of n simply meant you multiplied n copies of 2 together. That was the entire definition, and it was valid only for positive integer exponents.
Asking for 2 to the power of 1/2 would have been nonsensical. There is no way to multiply 2 together half a time using repeated multiplication alone. But later, mathematicians discovered a series of algebraic properties that exponential functions satisfy. Properties about how multiplying 2 powers adds the exponents, how dividing 2 powers subtracts them, and so on. These properties gave a consistent way to assign meaning to 2 to the power of any real number. The function was extended from positive integers to the entire real line, and the notation remained the same. Once the domain was extended to all real numbers, the input of 1/2 became perfectly meaningful. 2 to the power of 1/2 is the square root of 2, a definite, finite, well-defined value. The same function that once only accepted whole numbers now accepts any real input and produces a meaningful output. And so the extension of exponentiation gives us something clean and natural. Inputting 1/2 into the function 2 to the x gives the square root of 2. This is exactly the kind of result we are hoping to achieve for factorial, a real input producing a meaningful, finite output. What made this extension of exponentiation trustworthy was that the resulting function is perfectly smooth. No jumps, no breaks, no strange behavior. The graph of 2 to the x is a single flowing curve that passes through every integer value correctly and interpolates smoothly between them. This smoothness is not an accident. It is a consequence of the algebraic properties that motivated the extension in the first place. We will want this same property when we extend factorial. Now let us return to factorial and look for the algebraic property that will allow us to extend it. Notice that we can write n factorial as the product 1 times 2 times 3, all the way up to n minus 2, then n minus 1, and finally n. By writing it this way, we can see that the product 1 through n minus 1 appears as a natural prefix of the full product. Looking at the two expressions side by side makes the pattern obvious. The factorial of n is the factorial of n minus 1, with one extra factor of n attached at the end. The first n minus 1 terms are completely identical in both products. This gives us a compact and powerful identity. The factorial of n equals the factorial of n minus 1 multiplied by n. This is the recurrence relation for a factorial. It says each factorial value is simply the previous one scaled up by the next integer.
Rewriting this with the factors in the other order, n factorial equals n times the factorial of n minus 1. This is the standard form of the recurrence, and it is the key algebraic property that we will use to extend factorial beyond the positive integers. Now comes the crucial step. Instead of keeping n as a positive integer, we ask, what if we simply replace n with any real number x? The recurrence then reads, x factorial equals x times the factorial of x minus 1. We do not yet know whether this makes sense for non-integer x, but let us follow it and see what interesting consequences emerge. Let us test the recurrence by substituting specific values. If we set x equal to 1, the recurrence tells us that the factorial of 1 equals 1 times the factorial of 0. Now the factorial of 1 is just 1. That is a known value, so the right side becomes 1 times whatever 0 factorial is. From the equation 1 factorial equals 1 times 0 factorial, we can immediately read off the value of 0 factorial. Since 1 factorial is 1, we need 1 times 0 factorial to equal 1, which means 0 factorial must equal 1. This is the standard result that 0 factorial equals 1, and here we have derived it purely from the recurrence relation, without any separate definition or convention.
Now let us push further and substitute x equal to 0 into the recurrence. The equation becomes the factorial of 0 equals 0 times the factorial of negative 1. We just established that 0 factorial is 1, so the left side is 1. The right side is 0 times the factorial of negative 1. And here we immediately hit a problem. The equation says 1 equals 0 times the factorial of negative 1. But 0 times anything is always 0. You can never get 1 by multiplying 0 by some other number. This is a genuine contradiction, a bug in the system. The factorial of negative 1 cannot exist as any finite number. The recurrence simply breaks down at 0. If we continue further and substitute x equal to negative 1 into the recurrence, we get the factorial of negative 1 equals negative 1 times the factorial of negative 2. Since the factorial of negative 1 is already undefined or infinite, this equation just propagates the problem. The factorial of negative 2 is equally problematic. The same issue repeats at every negative integer. Substituting x equals negative 3 gives the factorial of negative 3 equals negative 3 times the factorial of negative 4. This chain of contradictions tells us something important. The extended factorial function will have poles, vertical asymptotes, at every negative integer. The factorial of negative 1, negative 2, negative 3, and so on are all infinite or undefined. The extension we are building works for all real numbers except the negative integers. Now let us try something more interesting. Substitute x equals 1/2 into the recurrence. The factorial of 1/2 equals 1/2 times the factorial of negative 1/2. This is remarkable. It tells us that once we know the factorial of negative 1/2, we can immediately find the factorial of 1/2 by multiplying by 1/2. The two values are linked. If we can determine either one, we have both. To find these values, we need a more powerful approach, a formula that can actually compute the factorial of any real number from scratch. Let us build one. We introduce two positive integers m and n, with n strictly greater than m, and we will carefully construct an algebraic identity that can be extended to real inputs. Starting from the recurrence, we can expand the factorial of m plus n step by step. Applying the recurrence once, the factorial of m plus n equals m plus n times the factorial of m plus n minus 1. Applying it again, the factorial of m plus n equals m plus n times m plus n minus 1 times the factorial of m plus n minus 2. Each application peels off one factor and reduces the argument by 1. If we continue applying the recurrence all the way down, stepping from m plus n until we reach m, we get a complete expansion. The product of those n consecutive integers sits in front, and the factorial of m terminates the expression. Rearranging, The factorial of m plus n equals the factorial of m multiplied by the product of the n terms from m plus 1 through m plus n. The underbrace highlights this clearly. To the right of m factorial, there are exactly n terms being multiplied.
By symmetry, we can write the same expression starting from the factorial of n instead of m. The factorial of m plus n also equals the factorial of n, multiplied by the product of the m terms from n plus 1 through n plus m. So, to the right of n factorial, there are exactly m terms, a perfect mirror of the first expression. Since both expressions equal the factorial of m plus n, they equal each other. The factorial of m times the product from m plus 1 to m plus n equals the factorial of n times the product from n plus 1 to n plus m. The factorial of m plus n has been cancelled from both sides, leaving a pure identity between products. Solving for the factorial of m, it equals the factorial of n, multiplied by the ratio of two products. The numerator is the product from n plus 1 through n plus m, that is m terms. The denominator is the product from m plus 1 through m plus n, that is also n terms. This identity is exact and holds for any positive integers m and n, with n greater than m. Now we introduce the plan for extending this to real numbers. We will replace the integer m with a real number x, so the formula should give us the factorial of x. But first there is a problem. The numerator has m terms in it, specifically m factors of the form n plus k, and once m becomes a real number x, we cannot simply count x terms. The solution is to let n grow to infinity. As n becomes very large, something beautiful happens to each factor in the numerator.
As n grows without bound, any factor of the form n plus a, where a is some fixed constant, becomes asymptotically equivalent to n itself. The ratio of n plus a to n approaches 1 because the constant a becomes negligible compared to the infinitely large n. This is an infinity over infinity situation, and by applying the rule for such limits, the ratio is confirmed to equal 1. This works for any fixed constant a. It does not matter whether a is 1, 3, or any other finite value. Every such ratio tends to 1 as n tends to infinity. Since every single one of those m factors in the numerator has ratio tending to 1 compared to n, we can replace each factor n plus k with simply n, multiplying all those factors together. The numerator product of m terms, each approximately equal to n, is approximately n multiplied by itself m times. And n multiplied by itself m times is simply n to the power of m. So in the limit as n tends to infinity, the entire numerator collapses to n to the power of m. The formula for the factorial of m now reads, the factorial of m equals the factorial of n times n to the power of m divided by the product from m plus 1 through m plus n. We now replace the integer m with a real number x throughout. The product in the denominator adjusts accordingly. Its terms become x plus 1, x plus 2, up to x plus n. The factorial of n in the numerator remains, along with the factor n to the power of x. We now write the limit symbol explicitly. The factorial of x equals the limit, as n tends to positive infinity, of the factorial of n times n to the x, divided by the product of x plus 1 through x plus n. This is the working definition we will use for everything that follows. Expanding the factorial of n as the product 1 times 2 times 3 all the way to n, and placing n to the x on the right, we now have a concrete function, call it f of x, defined by this limit. It takes any real input x and returns the value of the extended factorial. The task now is to verify it works correctly, and to compute the value at x equals 1/2.
Let us first verify the formula at a known value. Set x equal to 3. The function should output 6, since 3 factorial is 1 times 2 times 3 equals 6. So we substitute 3 into the formula and check whether the limit produces 6. With x equal to 3, the denominator becomes 4 times 5 times 6, continuing through 3 plus n. But the numerator also contains the factors 1 through 3 from the n factorial. So after cancellation, the numerator retains only 1 times 2 times 3, and the denominator retains only n plus 1, n plus 2, and n plus 3. The 3 factorial in the numerator, 1 times 2 times 3, can be pulled outside the limit since it does not depend on n. Outside the limit, we have 1 times 2 times 3. Inside the limit remains n cubed divided by the product of n plus 1, n plus 2, and n plus 3. As n grows without bound, this ratio tends to 1. The numerator and denominator both grow like n cubed, and their ratio approaches 1. So the limit equals 1, and the entire expression reduces to 1 times 2 times 3, which is 6. The formula correctly recovers 3 factorial. The verification succeeds. With the formula verified, we can also to plot the graph of this function over the entire real line. The shape that emerges is the gamma function, smooth and well-behaved for positive inputs, with vertical asymptotes shooting off to infinity at every negative integer. The positive side rises steeply, and the function interpolates smoothly between all the integer factorial values. The graph makes the behavior visible. For positive x, the function is a smooth, increasing curve that passes through all the correct integer values. At x equal to 0, there is an asymptote. At every negative integer, -1, -2, -3, the function blows up to infinity. Between consecutive negative integers, the function dips, creating a series of alternating arches above and below the axis. The domain of the extended factorial is all real numbers except the negative integers. Now let us use the formula for what we came here to compute. We have the complete definition of the extended factorial, and we are ready to substitute x equal to 1/2 and follow the calculation to its conclusion. Setting x equal to 1/2, the formula gives the factorial of 1/2 equals the limit of the product 1 through n in the numerator, divided by the product of 1/2 plus 1, 1/2 plus 2, 1/2 plus 3, and so on up to 1/2 plus n, all multiplied by the square root of n. Each term in the denominator is of the form 1/2 plus k, for k running from 1 to n. Adding 1/2 to each integer gives 3 halves, 5 halves, 7 halves, and so on, up to 2n plus 1 over 2 as the last term. So the denominator is the product of all odd integers from 3 through 2n plus 1, each divided by 2. Pulling all the factors of 1/2 out of the denominator, there are n of them, produces a factor of 2 to the n in the numerator. The denominator becomes simply 3 times 5 times 7 through 2n plus 1 with no fractions. The product of 1 through n multiplied by 2 to the n can be rewritten. Each factor k in the product 1 through n, when multiplied by the corresponding factor of 2, gives 2k. So the numerator becomes the product of all even integers from 2 through 2n. This is now a beautifully clean expression. The product of all even positive integers up to 2n divided by the product of all odd integers from 3 up to 2n plus 1 times the square root of n. This form is extremely suggestive. It looks very close to a famous classical infinite product. And indeed it is. There exists a classical result known as the Wallace product, which states that the infinite product 2 over 1 times 2 over 3, and so on, equals pi over 2. This product was discovered by the English mathematician Wallace in the 17th century, and it gives one of the earliest known expressions for pi as an infinite product of rational numbers. Writing the Wallace product in limit form, the limit as k tends to infinity of the product of fractions 2 over 1, 2 over 3, continuing all the way through 2k over 2k minus 1 times 2k over 2k plus 1 equals pi over 2. To connect the Wallace product to our expression for the factorial of 1/2, we rearrange the Wallace product. Instead of writing each even integer as 2 separate fractions with the 2 adjacent odd integers, we group the 2 occurrences of each even factor together. This gives the square of the ratio of even products to odd products times a remaining tail factor. Taking the square root of both sides, the product of even integers over odd integers times 1 over the square root of 2k plus 1 equals the square root of pi over 2. Rearranging the denominator, we bring the factor 2k plus 1 into the denominator of the main product and compensate by multiplying through by 2k plus 1 divided by the square root of 2k plus 1, which simplifies to the square root of 2k plus 1. Now we split the square root of 2k plus 1 into 2 pieces, the square root of k multiplied by the square root of 2k plus 1 divided by the square root of k.
This splitting is deliberately designed to isolate something familiar. Look at what we now have inside the limit, the portion consisting of the product 2 times 4 through 2k, divided by 3 times 5 through 2k plus 1, times the square root of k. This is exactly the expression we derived for the factorial of 1/2 from Gauss's formula, with n replaced by k. That portion is the factorial of 1/2.
We can therefore separate the two limits, the factorial of 1/2 times the limit of the square root of 2k plus 1 over k equals the square root of pi over 2. The second limit, the square root of the ratio of 2k plus 1 to k, can be evaluated independently. As k tends to infinity, 2k plus 1 over k approaches 2, so the square root of that ratio approaches the square root of 2. Substituting, the factorial of 1/2 times the square root of 2 equals the square root of pi over 2. Now we divide both sides by the square root of 2 to isolate the factorial of 1/2. Dividing the square root of pi over 2 by the square root of 2, we get the square root of pi divided by the square root of 2, divided by another square root of 2 in the denominator, which simplifies to the square root of pi divided by 2. The factorial of 1/2 equals the square root of pi over 2. This is the central result of this video. The pi that appears here emerges from the Wallace product, which connects the ratio of even and odd integers to the geometry of the circle in a deep and beautiful way. Having established the main result, we now turn to a bonus derivation that reveals an even deeper structure. Let us look at Gauss's formula once more and observe what happens when we multiply the factorial of x by the factorial of negative x. Gauss's formula applies to any real input, including negative x. We write the formula for x factorial, with n to the x in the numerator and factors x plus 1 through x plus n in the denominator. We also write the formula for the factorial of negative x, with n to the negative x in the numerator and factors 1 minus x through n minus x in the denominator. Now we multiply these two expressions together. When we multiply the two formulas, the factors of n to the x and n to the negative x cancel each other, since their exponents add to 0. The numerators combine to give the square of the product 1 through n. That is, each integer from 1 to n appears squared. The denominator becomes the product of all factors of the form k squared minus x squared, for k running from 1 to n. Each denominator factor k squared minus x squared can be factored and rewritten. Dividing numerator and denominator each by k squared, the factor k squared minus x squared becomes k squared times the quantity 1 minus the square of x over k. After the k squared values cancel with the squared product in the numerator, what remains in the denominator is simply the product of factors 1 minus x over k squared, for k running from 1 to n, all in the limit as n tends to infinity. Taking the reciprocal, 1 divided by the product of x factorial and the factorial of negative x equals the infinite product of factors 1 minus the square of x over k, for k from 1 to infinity. To identify this product, we recall a classical result from the study of the sine function. The sine function has the Taylor series expansion. This is an infinite polynomial in x, and its zeros, the values of x where it equals 0, occur at 0, positive and negative pi, positive and negative 2 pi, and so on, through all integer multiples of pi. Plotting the sine function confirms this. The curve crosses the horizontal axis at exactly 0, plus and minus pi, plus and minus 2 pi, plus and minus 3 pi, and so on forever in both directions. For an ordinary polynomial, once you know all the roots, you can write the polynomial as a product of linear factors, one for each root. Euler applied this same reasoning to the sine function, treating it as an infinite polynomial. He wrote the sine as a constant c times x times the product of all pairs of conjugate linear factors, x plus k pi and x minus k pi, for k from 1 to infinity. The constant c is unknown at this stage. It needs to be determined from additional information. Everything else in the factor expression is determined by the zeros, so our task reduces to finding the value of c. Each conjugate pair, x plus k pi times x minus k pi, is a difference of squares, which equals x squared minus k pi squared. So the factored form simplifies to c times x times the product of x squared minus pi squared, and so on. Dividing both sides by x, the sine of x divided by x equals c times the product of all factors x squared minus k pi squared, for k from 1 to infinity. The factor of x has been cancelled from the left side.
To find c, we let x tend to 0. The left side, sine of x divided by x, approaches 1 as x tends to 0, by the standard limit that the ratio of sine x to x equals 1 at 0. On the right side, every factor x squared minus k pi squared approaches 0 minus k pi squared, which is negative k pi squared, as x tends to 0. Solving for c, it equals 1 divided by the product of all those negative squared values. This is an infinite product with a specific value, which we now know is the value that makes the entire sine formula consistent. Substituting c back in, the sine of x divided by x becomes the ratio of the product of x squared minus k pi squared over the product of negative k pi squared, for k from 1 to infinity. Each individual ratio of x squared minus k pi squared over negative k pi squared simplifies in a clean way. Factoring negative k pi squared out of each numerator factor, x squared minus k pi squared divided by negative k pi squared equals 1 minus x over k pi squared. So the entire product collapses to the product of factors 1 minus x over k pi squared, for k running from 1 to infinity. This is Euler's sign product, one of the most celebrated infinite product formulas in all of mathematics. Now we make a substitution to align the two formulas, replacing x with pi x throughout the sign product. The sine of pi x divided by pi x equals the product of factors 1 minus x over k squared, for k from 1 to infinity. The denominators are now just the positive integers, 1, 2, 3. No factors of pi appear. At this point, place the two formulas side by side. Since the two expressions are equal, we can write 1 divided by x factorial times the factorial of negative x equals the sine of pi x divided by pi x. Taking the reciprocal of both sides gives us the reflection formula. X factorial times the factorial of negative x equals pi x divided by the sine of pi x. This is one of the most beautiful identities in all of mathematics. It connects the extended factorial function, an object built from products of integers, to the sine function, an object built from geometry and circles. Yet here they are, linked by this single elegant equation. Now we substitute x equal to 1/2 into the reflection formula. With x equal to 1/2, the left side becomes the factorial of 1/2 times the factorial of negative 1/2. The right side becomes pi times 1/2 divided by the sine of pi times 1/2, which is pi over 2 divided by the sine of pi over 2. The sine of pi over 2 is exactly 1, so the right side simplifies immediately to pi over 2 divided by 1, which is pi over 2. The product of the factorial of 1/2 and the factorial of negative 1/2 equals pi over 2. We now have two equations involving the same two unknowns. The second equation comes from the recurrence relation established earlier. The factorial of 1/2 equals 1/2 times the factorial of negative 1/2. Substituting the recurrence into the product equation, 1/2 times the factorial of negative 1/2 squared equals pi over 2. This gives the factorial of negative 1/2 squared equals pi, so the factorial of negative 1/2 equals plus or minus the square root of pi. And from the recurrence, the factorial of 1/2 equals plus or minus the square root of pi over 2. We need to resolve the sign. The sign is resolved by returning to Gauss's formula. Looking at the formula for the factorial of 1/2, the numerator is a product of positive integers. The denominator is a product of positive terms, since every factor 1/2 plus k is positive, and n to the 1/2 is positive. Every single piece of the expression is strictly positive. Therefore, the limit must be positive, and the factorial of 1/2 must be strictly greater than 0. The factorial of 1/2 equals the square root of pi divided by 2, positive. The factorial of negative 1/2 equals the square root of pi, also positive. These are the final results, established through two independent methods, first through the Wallace product, and now confirmed through the reflection formula and the Euler sign product.